Today we're going to be learning about rate laws, so let's get right at it. Here I've got some data for you. So far we've looked at rates of reactions, which is what you can see on this far right side. And now what I want to talk about is how do we know when you double a concentration it might double the rate, or would it triple the rate, or would it not even change the rate at all? That's kind of what a rate law will tell us. So let's take a look at the data here. If I've got an equation in which I've got NH4 and NO2, normally when I put these together and if I change a concentration of something, we know that there'll be more collisions. More collisions should lead to a faster reaction. Now that's not true every single time. Let's see if that's the case here. So take a look, I've got NO2 in this middle column and NH4 in the left column. I can see right here off the bat that these are kept the same. So the only variable that I'm changing in this is not temperature at all, because it's all at 25 degrees Celsius. I'm just changing the concentration of my NH4. I've doubled it. It went from 0.01 to 0.02. So if I've doubled the amount of NH4, does that change the actual rate of the reaction? Let's take a look at the far right-hand side. And yeah, I can see that it actually doubles it. I know that these 10 to the negative stuff kind of trip people up a little bit, but notice it's all 10 to the negative 7, so I can kind of ignore it a little bit. And I can see that 5.4 goes to 10.8. That's doubling it. So I can see I doubled concentration, and it doubled the rate of the reaction. That tells me something about the rate law. The next part I'm going to look at is I'm going to see what happens when I have NO2 and when I change that. Okay, so another spot. Let's take a look at this spot right here. These are the same. And if I look over here, I have doubled it when I look at experiment 2 to 3. I doubled the concentration, and again, I doubled the rate. So this makes complete sense. Now in the AP world, not everything makes sense, of course. But so far, let's keep it simple. I'm going to keep it same on this last column here. And take a look at when I double the concentration of my NO2. I actually double the rate of it also. So everything seems to be working out perfectly and lovely. We got to start with a simple one at the beginning. So we're talking about rate laws today. And the rate laws will tell us, if you double something, what happens to the rate of the reaction? Does it double it? Does it quadruple it? Or does it go slower? It can do that sometimes. Like, take a look at this one. These ones are the same. This one, I doubled it, but the rate of the reaction did nothing. In other words, the rate of the reaction isn't dependent on my OH at all. It doesn't have anything really to do with it, it seems like. This seems kind of weird, right? We've got to get a little further into this part. Okay, so far in your world, you should be able to see I'm keeping things the same in one spot, and I'm doubling something in another spot, and then I'm taking a look at what happens in the rate. And here, I did that same thing. I kept something the same, I doubled a different thing, and I saw what it did to the rate. If you got that, you're doing great so far. Let's get through some, vocabulary. So the rate law for this first thing we're looking at looks like this. So notice what we got, NH4 and NO2. Those are the two substances from this beginning thing, NH4 and NO2. So the rate law for this would be a first order for NH4. It's called a first order because there's a technically little 1 right there, right? You could have a 1 or not have it there, it's implied. And it's first order for NO2. What that means is if you double the concentration of it, it will double the rate of the reaction. Okay, let's look at this example here. So rate equals K, that's a constant, times these bracket things means concentration. Concentration is molarity. So in other words, if I take something and I have a concentration of NH4 of maybe like a 1, well, I'm going to get a set rate when I plug in all of my values. If I want to change the concentration of NH4 and let's say double it to 2, then I can see if I plug in the numbers, my rate will double by 2 also. That's what a rate law is going to tell us. It tells us the math part. If you double something, what happens to the rate of the equation? Vocabulary. We would call this a first order according to NH4, first order according to NO2, and overall this is a second order reaction because 1 plus 1 equals 2. Let's practice that here. At this point you should be able to do this part. So hit pause, try these problems, and then see what my answers are. You can even go fast through my words and just look at the answers. I'll write them on the board. So try them on your own and then watch this. That's the way I would suggest to do it. Okay, here we go. I've got my rate law right here. This is the important part. I've got my equation, but actually that doesn't matter so much as the rate law. It says, what are the reaction orders in this rate law? So in other words, this is, see that little 2 there? This is second order for NO. And there's a 1 there, first order for H2. And overall, 2 plus 1 equals 3. Overall, this is a third order reaction. As simple as that. Let's take a look at B. It says, does doubling the concentration of NO has the same effect as doubling the concentration of N2? My answer would be no. And that's because if I look at the rate law, I'm going to write it down here to make it clearer. If I take this whole thing and I have a doubling of the reaction, in other words, I go from all of these equaling 1, and now let's change it to equaling 2. If I put a 2 here with H2, that'll double the rate of the reaction. But if I put a 2 here in place of NO, it'll do 2 to the second. That'll 4 times the rate of the reaction. So my answer to this part is no. It does not have the same effect. And I know that because the rate law tells me so. Okay, let's take a look at this one. You should also be able to do this part too. So if you want to pause it and take a look at it, and then come take a look with me. We're trying to rank these mixtures in order of increasing rate of the reaction. And again, our rate law tells us this. So let's take a look at the rate law. It's at the top here. Here's my rate law. They give me the equation too, but notice how I'm not using the equation at all. It's not useful in the case of these examples. So A is represented by the red ones, and B is represented by the purple ones. So we're trying to rank these in order of the increase in the rate of the reaction. In other words, is the fastest rate of the reaction going to be equal amounts of A and B? Or is it faster to have more of one substance versus the other? So I'm actually going to plug in kind of values. Rate equals K. Remember, K is called a rate constant, and we'll get to this part. I'm going to times it by A and B. Now in this case, my A is the red stuff. So I have 1, 2, 3, 4, 5. 5. My B is the purple stuff. And I happen to have 1, 2, 3, 4, 5. 5 purple. So in this case, when I wanted to calculate what that would be, I would say rate is equal to 5 times 5. Whoop, I almost made a mistake. I hope you caught it. Squared. That's my rate law here. So 5 squared, so in other words, this is like 5 cubed. Oh, come on, math. 5 cubed is 125. 125K is my rate there. Let's take a look at that middle one. My rate is going to be equal to my K, the number of red ones that I've got. I've got 1, 2, 3, 4, 5, 6, 7, times the purple ones, but squared. 3 squared. As you might imagine, having 3 squared is not as powerful as having that 5 squared from before. So my rate in this case, if I equal out that math, is 63K. This one is definitely slower, because having more purple, or the B ones, will increase the rate of the reaction more significantly than my red ones. All right, last example. Rate equals K. The number of red ones I have is 3. The number of purple ones I happen to have, I believe, makes me 7. That's 7 squared, though, so I think you can see where this is going. My rate is then equal to 147K. This one right here, when K is the same in all cases, K is our rate constant, this one will be the fastest, because you have the most of it as the B, and the B is going to be squared according to the rate law. My slowest is the one that I have more red, and I guess that makes this one over here in the middle. Here's the work for you. Okay, so far hopefully you're getting the idea of what a rate law is. We can actually plug in numbers and see how fast the reaction goes. The other thing that I hope you're seeing is that we're completely ignoring the actual reaction. In other words, take a look at this. N2O5, there happens to be 2 of them. But if you look over here, that's not a 2 there. You cannot use the balanced equation to find yourself the rate law. The rate law can only be found using data. And that was what I used at the very beginning with that chart. We can only use data. Take a look at this one. This one has a 1 and this one has a 1. Well, this one happens to have a 1 right there. That's just coincidence. But this has a 1/2. That's weird too, right? The moral of this slide is you must use data to get these rate laws. The other part is, yeah, you can have fractions, 1/2, and you can have negative numbers. If you think about it with a negative number, what that means is I add more N2O5 and it goes slower. That should make you feel a little weird, right? Completely against whatever you learned in your first year chemistry. But we'll talk about why that is next week or the week after that. It'll have to be the week after that because that'll be about mechanisms. So hang in there. Right now you're just trying to use the data to get there. That's what this is. I'm going to do this problem with you. Oh, we've got K to solve for, and then I'm going to do this problem with you. Then you're going to do practice, and by the end of practice, you're going to be awesome. Okay, this is the original data from the very first slide that I showed you. We're looking at the same stuff, NH4 and NO3. And we're finally going to talk about this K. The K, again, is called the rate constant. And what I'm going to do is solve for the rate constant. If you notice, I'm just going to call that rate constant K, or in other words X, that's my variable, and I'm just going to plug in numbers for all the rest. I could use experiment 1, where I'd just put 0.01 for here. This NO2 would be 0.2, and then my actual rate, 5.4 times 10 to the negative 7. I just put in the numbers. Now, one thing to know is that this is the rate of the actual reaction, not the rate of K of NO2 or the rate of NH4, but the rate of the entire reaction. So that's a key part. If I do this, I will solve for K, that is 2.7 times 10 to the negative 4. Now I'm going to do it in a different way. So that was using the first lane. But what if I used lane 5 right here? What if I use lane 5's data? Then I'd have 0.2, I'd have 0.04, and I'd have 21.6 times 10 to the negative 7 for the rate. What would be my K then? Hopefully you're thinking it'd be the same. Yeah, because it's a rate constant. You're right. Constant makes me think it's the same. And again, it's 2.7 times 10 to the negative 4. You can pick any lane you want, any experiment number you want. You put the numbers in, you will always get the same K. If it's perfect, of course, theoretically speaking, right? Now, what I want to talk about past this is what kind of units do we have? So you were probably just like, yeah, that makes sense, we're good, but you didn't even think about units. That's okay, nobody ever does. Let's think about units now, though. So I know my rate, I'm going to look at just units, is in molarity per second. It tells me that right here. And that's going to equal K. That's the one I want to find for units. This thing right here has units of molarity. This thing right here has units of molarity again. So now I'm trying to figure out what are my units for K. This molarity times molarity, I'm going to divide both sides by that. In other words, molarity squared. And I get molarity squared over here, right? Because I'm dividing both sides by molarity squared. So that when I simplify this out, this molarity on top goes away, and I'm left with just one molarity on the bottom. So my rate constant really has units of molarity times second all on the bottom. Or another way that you could write that is molarity to the negative 1, seconds to the negative 1. Whichever way makes you happy is fine with me. So when we're finding the constant, we need to know the actual number and the units. That can be the trickier part. All right, let's sum it all up. I'm going to do everything you should need that you are should be able to do after this video right here in this problem. And I have about a minute to do it in. I'm going to have to go fast. I'm sorry. I need to find the rate law for the reaction. Okay, so I'm going to keep this the same. And I'm going to double this, it looks like. And it looks like I kept this the same. So in my head, I'm thinking, okay, 2 to the what equals that divided by that, 1. 2 to the what equals 1. The question mark would equal 0. Any number to the 0 would equal 1. In other words, it has no effect on the rate. So far my rate law is rate equals K. They all start out that way. Times, here I'm doubling B to the 0. I've got 1 so far. Times my A. All right, I got to find where they're the same for B. Here to here, 0.1 to 0.1, that's the same. But here to here, I've doubled it by 2. Then I go 4 to 16. It's not doubling it. I'm thinking in my head, 2 to the what equals 4. Because 16 divided by 4 equals 4. 2 to the what equals 4? 2 to the 2. This question mark is equal to 2